This last section we're going to be looking at now, we are looking at, once again, volumes of revolution. These are going to be washers, so they're hollow, but they're no longer just around the x or y axes. Okay, in this next step, these volumes of revolution are going to be, they will now be around lines. So vertical or horizontal lines, right? So vertical or horizontal lines. So they're going to be the same direction as the x and y axes, okay? So the direction of rotation will determine if the integral is going to be with respect to x or y. So in other words, if you're rotating in this direction, right, that's like kind of like going around the y-axis. That would be dy. If you're rotating it in this direction, which would have been, right, around the x-axis, right, this is going to be dx. Okay, so around horizontal lines, it's still going to be dx, but if it's going to be in this direction, it's going to be dy. So let's consider the first quadrant area bound by this. So y is equal to 3 is a horizontal line, x equal is a vertical line, square root of x plus 4. Okay, so square root of x plus 4. I know the square root of x looks like that. It's just been moved up 4. Okay, so here's what we're going to do. See if we can actually draw this thing kind of accurately. So it's going to be, oh no, it's got to be better than that. It's got to be something that's going to look like this. Okay, so, and 1, 2, 3. I'm only going out to 3 in the x direction. So there's 3, and there's 3 for my y direction. So really, this is the region that we're going to be talking about. Let's take a look at this. So this is this region here. It's kind of like a quadrilateral. It's got 3 sides, but one of these sides is a curve on the top, right? So 1, 2, 3, 4. So this is the region that we're talking about. So from 0 to 3 in the x direction, and well, from 3 up to, I don't know this value. We'll actually figure this out later. But that's in the y direction. So first off, we're going to rotate it around y is equal to 2. Now y is equal to 2 is a horizontal line here, right? It's around there. So it's not going to go around the x-axis. If it was around the x-axis, it'd go all underneath. This is going to be an empty space, and so I'm going to get a mirrored rotation. It's going to be down here. Let's see if we can actually draw this thing. Okay, so what can I actually draw that's kind of accurate? Okay, so 1, 2, 3, 4. So y is equal to 2 is my axis of rotation, or axis of spinach. That's where I'm going to be spinning it around. Y is equal to 2. So this thing is up 1 from there, so it goes from 3 to 4, and it's going to be this kind of shape, right? So that shape is going to get a mirrored image. So this one is going to go to here. I'm going to get the mirrored image. One, I'm going to get something that looks like this. And then, of course, this is all going to be round. So yeah, I'm going to get basically something that looks like this. Okay, so I've kind of drawn it invisible, but I can see it's centered around y is equal to 2. This is my axis of rotation. This up here is going to become this down there. So maybe I actually can draw this thing with a little bit of reality. Right, so I'm going to see that part. And that part. The rest of this is all going to be basically, so it is hollow. That's going to be basically an invisible line in behind. Okay, so let's see if we can set this thing up. I know that the volume of this thing is going to be pi integral squared. Okay, it is in the same direction as x, so I'm going from 0 to 3. 0 to 3 dx. And I do know it's hollow, so it's going to be the outside squared minus the inside squared. Okay, well the outside squared, this is where it gets a little bit confusing. Because it's now the function, whenever we're talking about the function, we kind of mean from the x-axis up, right? That's exactly what this is. Yeah, so if I'm going to say the original function, that's this, right? This distance here from the x-axis up to there, that's the outside. But I don't want to go from there. I only want to go from here. So it's going to be the entire function minus this part. See? So that's the part that I want to get rid of. Let's see if I can get rid of part of that. really, I want to get rid of this part here. See that? It's the entire distance except for this. Okay, so here's really what it's going to be. This is going to be the function. And the function was, what was the function? It was, right, this is my function. This is the square root of, square root of x plus 4. That's what this distance is. So this is going to be the square root of x plus 4 minus off that 2. Root x plus 4 minus 2. Now, I know that that's just going to be positive 2, but show that as the function minus 2, right? Because that's the 2 that I'm subtracting off. I'm subtracting off that part. Because I'm not going from the axis all the way up. I want to go from the center of rotation, right? I want to go from this line, this level of 2. Okay, so that's the outside. Now, let's do the inside. Okay, so the inside, I'm going to do that in a different color. Let's do that one in green. The inside is from here to here, here to here, here to here, here to here. So it's a constant. Oh yeah, because it's just a flat line. This thing's got a cylinder. So it's the distance from 2 up to, it's the distance from 2 to 3, right? It's a constant 1. It's this constant distance here. So the axis around which I'm rotating up to the inside function, which is this flat line. So this is actually, if you think about it, it's the distance from 3 down to 2. It's 3 minus 2. Now, big deal. We know that that's going to be 1. This is a constant distance of just 1 all the time. Okay, so now we can actually clean this stuff up. What do we got? This is going to be from 0 to 3. So this is square root of x plus 2. Root x plus 2, it's being squared, minus 1 squared, the x. So you know what? Yeah, at this point now I can just expand this stuff all out. 0 to 3, this is going to be root x squared. So x plus 4 root x plus 4 minus 1 plus 3 dx. Now we can do our antiderivatives if we really want to, right? You know what? I'm just going to be plugging this into a calculator. So I'm just actually figuring out this area. Now I'm going to graph this on my calculator. I have no idea what it looks like. I don't care. It's not this. This is a volume, right? And it's not this. This is a combination of different things that I've put together. So all I care about is I'm just going to do the area from 0 to 3. So whatever this is, I think this turns out to be 85.9. Done. There's no units for these, right? This is just cubic units, whatever that is. So, but that's the shape that I'm going to get if I go around y is equal to 2. Now, it is hollow because it's not actually touching, right? There's the inner function, and here's the axis of rotation. It's not actually touching. Now, if it was touching, it wouldn't be hollow, and it wouldn't be this thing minus this thing. This would be gone because there would be no hollow part. Okay, let's try this. Let's rotate it around y is equal to 8. Hang on, it's still going to be horizontal. Y is equal to 8. Oh, y is equal to 8 is like way up here. Oh, okay, that's going to give me a different kind of thing. Once again, let's see if we can draw this thing. 1, 2, 3, 4. 3. So yeah, it's this kind of shape here, right? 5, 6, 7, 8. 8 is here. So this is going to be kind of strange. This is the line around which I am rotating. That's my axis of revolution. So this stuff is not going to go down. It's actually going to go up. I'm going to get a mirrored image up here. Kind of looks like the same thing. It's going to look something like that. See, mirrored image. I got a little flat section, curve, curve. So it's going to be, oh, it's going to look kind of like this. This is an odd shape. It's almost like if you turn your head sideways. This is kind of like the Roman Colosseum. It's kind of like, if you think about it, as a hockey puck, right? Now it is hollow. There's the base, and you can see it's been hollowed out, and it goes up to, this is going to have a ledge here too. So these are kind of hard to see, kind of hard to draw. I'll try and redraw it over here because I know what it looks like. I know it's going to look something like this. But yeah, so from your invisible diagram, or invisible lines, and this thing's going to have solid lines on the outside, okay? I need to be better than that. So in some ways, it's kind of like a hockey puck. And this is going to be coming into there. So it's a smaller hole there. So it's going to be a shape kind of like this. Okay. It's not the important thing that you can draw these things well. I obviously cannot draw them very well, but from my diagram, I'm going to figure out my formula, or I'm going to figure out the equation here, or not the equation, but the what we're going to get for a volume. So I know it's going to be circular, so that's why I've got pi. It's still going around the dx position, so it's still going to be dx. And it is hollow, so it is going to be, okay, so hang on. So from 0 to 3, it's going to be the outside squared minus the inside squared. Okay, so what is the outside squared? Good question. If you look at the diagram, if you look at where we are, the outside is from the axis of rotation. It's not up to here. No, 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 no. It should be down to here. Well, aren't they the same thing? Yes and no. Right? I don't know the equation of this stuff here at the top. That's my mirrored image, right? That's my image. The stuff that I started with is down here. This is what I started with, so I actually know this. So this we can actually figure out. Okay, so let's get back to here. Oh, no, that's not very good. This is going to take forever. Stroke. Okay, so let's see if I can get this thing. I know that the distance from here all the way up to here, right? I know the distance from here up to here is the function. What I want is from here down to here, or here down to here, if you will. The outside is going to be from the center all the way down to here. So maybe I'll do the outside one first. We'll get rid of all this stuff and we'll bring it back in. We'll do the outside one first. The outside is from here down to here. As I'm integrating from 0 to 3, right, it's just a constant 8 down to whatever this line is. This is 3. 8 down to 3. So it's just constant. That's why I have a constant outside edge, right? See, oh yeah, it's kind of like the Roman Colosseum or a hockey puck or whatever. So this is really the distance from 8 down to 3. I know it's 5. Really, it means this. It means the full distance of 8 minus this distance of 3. That's how you understand adding and subtracting, right? 8 minus 3, or 8 minus 5. 8 minus, oh, why am I going to mess this up? This is 8 minus 3, which we know is going to be 5. Okay, next. It's from the center, the axis of rotation, down to here, right? So it's down to the curve, down to the curve. Now, I don't know that. I do know that the distance from the x-axis up to here is the curve. That's the function, right? This is the function from the x-axis up. So it's going to be the full distance all the way up to 8 minus this part, and that'll give me this left over. And that's what I want. So it's the full 8 minus the function. So this is going to be 8 minus whatever the function was. And the function was the square root of x plus 4. Square root of x plus 4. So that's what this is going to turn out to be. Now you could just say, oh, it's always going to be 8 minus. No, depends. Depends upon if it's above or below. If it was below, in this case we had to add on or subtract pieces off. Here it's going to be, yeah, so here we subtracted off the 2. Here it's going to be 8 subtract the function. It's different. And sometimes it's actually lower. If I put my axis of rotation down here, I'm actually making it longer. In that case, I'd have to add it. So that's why it's so important to try and draw some form of ugly diagram like I've got here. So the outside squared, so 8 minus 3 squared, which is going to give the, okay, so from 0 to 3, 8 minus 3 is 5. This is just a constant distance of 5, right? 5 squared, which is 25, minus. This is why, quite often, let's see, we got 8 minus the square root of x minus 4. So in other words, this is going to be 4 minus the square root of x, and then it's all being squared dx, right? So that's quite often why, if it's a simple function, this isn't all that bad to figure out, right? Pi from integral from 0 to 3, 25 minus 4 squared is 16. 4 times root x is doubled is 8, and it's going to be minus, it's plus 8 root x, and root x squared is, so this is going to be minus x dx. We could figure these out. It's not that hard. And once again, this is just going to be, I think it's 157.7 when you do it on your calculator. You don't need to do the antiderivatives of this stuff. And in fact, you could plug this in as long as you had the right brackets. If you plug it in wrong, you're never going to know. So you know what? I suggest you simplify it out. But quite often, if this is going to be some function squared, quite often that makes it something way harder than we can actually do by hand. Okay, let's get into the most difficult one here. Now we're going to rotate it around x equal to 5. X equals 5 is a vertical line. So it's going to be in this direction, which means it's going to be dy. Okay, so let's see. This is the shape we're going to be doing, and we're going to rotate it around x equal to 5, which is over here. So that's going to go over there. We're going to get some kind of weird shape that looks like this. It's hollow. Hey, it's kind of like a bunt pan or something like that. It looks like a cake, but it's also been hollowed out. Okay, so see if we can draw this thing. One, two, three, four. Pew. 3. 1, 2, 3. Okay, and this is going to be going around x equal to 5. 4, 5. Okay, so remember, here was our weird little shape, right? This is where we're going to be rotating around this axis, if you will. So it's going in that direction. So this distance of 2 is going to go to a distance of 2. I'm going to get a mirrored image over here. And then, oh, I'm kind of off a little bit, but you get the idea. This is going to be round in this direction. There's the entire base all the way around. Oh, terrible. And this top, you can't really see it, but there's a solid edge there, which means there's going to be a solid edge that goes all the way around to there. So this is kind of like a band, a round band, as I'm destroying this diagram. And then this is the curved part. So it's kind of hard to see. But I do know that I've got a hollow center, and I can see the inside and the outside. Okay, so let's see. First off, I know it's going to be the volume. What do we got? It's going to be pi. So from 0 to 0, hang on, 0 to where? Oh, no, it's going to be dy. So remember that y is equal to the square root of x plus 4? I need to express this as a function of y. So in other words, y minus 4 is equal to the square root of x. In other words, x is equal to y minus 4 squared. That's my f of y. F of y is equal to y minus 4 squared. So where is that? Y minus 4 squared is this part of the curve, right? I'm going to start here. So I'm integrating to y. So from here to here, it's all along this flat. I'm not onto the curve yet. So from here to here, this first part, I'm going from 0, sorry, not from 0, from 3 to 4. So the first part, doing dy from 3 to 4, it's just this, it's a constant flat line. So it's kind of like our previous one where we had the flat walls on the outside and then the curve on the inside. Same thing. This first part from 3 to 4, it's just going to be the outside and the inside. So the outside, let's see. If we do the outside is from the axis of rotation, which is 5, all the way back to the x-axis. So it's 5 minus 0. This is 5 minus 0. In other words, it's just 5 squared. It's a constant distance of 5, right? From 5 all the way back to here. Because that's where we're rotating around. Now, what about the inside? The inside is from 5 back to 3. And that's just always a constant 5 minus 3. That's just a constant 2. It's always a constant 2. So minus 5 minus 3, boop, squared. And this is going to be dy. So that's the first part. I'm integrating from 3 to 4. Now I'm going to integrate along the curve here. So from 4 up to, I don't know this value. Oh yeah, that's the idea that way back this thing that we started off when the x value was 3. What's the y value here? Well, it's going to be the square root of 3 plus 4. And the square root of 3 plus 4 turns out to be around 5.73. close to that. So 5.73. So you know what? I'm just going to do this on my calculator as around 5.73. Now, yes, I know that's the square root of 3 plus 4. You could actually plug that in pretty accurately. So I'm going to integrate from 4 up to that point. So this is plus pi. So from 4 up to root 3 plus 4, which is 5.73. Okay. Once again, let's look at the outside and the inside. The outside is the distance from here, so from the axis, all the way back to there. It doesn't go all the way to the x-axis. Now, this is the height under the curve. This is f. But it's not f of x. This is f of y, right? The distance from here up to here is f. So I want to go all the way out to 5. So I want to go 5 back to here. So it's going to be 5 minus the function, right? So if I go 5 minus the function, it'll give me this part, because that little part that I just put in there, that is f. So it's going to be 5 minus the function, because it's going 5 backwards to it. Okay, so let's do it. 5 minus my function, and my function is y minus 4 squared. And that whole thing is squared. Yikes. Now, minus the inside. Now, luckily, the inside from here back, see, it's still a constant 2. It's just 2. It's, yeah, this whole section, this is all just constants. So it's 5 back to 3, 5 back to 3, 5 to 3. So 5 back to 3, 5 minus 3, which is 2, squared, dy. You can see why I'm not going to be expanding these things out and doing them beautifully by hand. No. Now, this one's actually not that bad. So, okay, so we should finish this up. Pi, the integral from 3 to 4. This is 25 minus 2 squared, which is 4. So this is going to be the integral of 21. So this turns out to be 21 pi dy. That one's nice. Plus the integral of, yeah, this is not going to be turning out to be very nice. So I plug this one into my calculator. It's going to be pi times 22.17 approximately. So I've had to round this stuff off. So this whole thing turns out to be around 135.6. Whew. Okay, so that is why this one is so more difficult, because doing in the dy direction, sorry, in this direction means I know it's got to be dy, which means my function needs to be turned into a function of y, no longer a function of x, right? So I have to solve for x equal to, and that's my function of y. So now when I'm talking about function, it means the distance from here up to the curve. Okay, so that's why I'm going from 5 back to there. It means it's going to be 5 minus the function. So yeah, in this case, it was 5 minus the function, and the function's got to be a function of y. Once again, this would probably be like a 4-mark question, like 1 mark for some kind of a diagram, probably 1 mark for the inside function. You're going to have to figure out this number on your own, 1 mark for this, and then we're not really showing all that work in between here. That's just a whole bunch of ugly algebra. We know we're going to be plugging it into a calculator. And that is the end of the volumes of rotation. So there's one more section called volumes by cross section that we're not going to do at all. So pretty much this is the end of chapter 6. Later on in the week, I'm going to give you guys a practice thing just to look at. Maybe we'll do a quiz, but we're certainly not going to be doing a full test on this one. Alrighty, good luck with these.